morning. Let's start. Yeah, how's it going? People look at the homework, like the problem set. Is it okay? Any questions? Yeah, so please look at the homework and let me know if you have any issues. And also in the programming assignment, please take a look and try to get started because it will take some time. But you still have a few weeks, so it's not extremely urgent, but like it's better to at least look at it because it will take more time than the first one. Yeah. So today we're doing embeddings. Sorry. Today, yes. It is Pythonic sort and communication primitives. I don't remember which lecture number, but it goes, yeah. It doesn't. It's up to, but not including sample sort.
Okay, so we should be able to do that.
Yeah. Yeah. The next homework will be about embeddings, but after today, you should be able to do it. But the next one is not coming out for another week or something. So, yeah, you should have everything that you need to do it. Yeah. So today we're doing embeddings, and embeddings are like you have a topology, like a network topology, for example, like a hypercube, and you want to so you have like an algorithm that is described for some kind of network topology, for example, I don't know, a ring or a hypercube or anything, but you actually have a different network topology, like in your actual machine, and you want to map the described algorithm into the topology that you have, and you want to make some kind of theoretical claims about how efficiently it will run. And the way you can do that is you map, so you can think of just a topology as a graph that connects the nodes, which are the processors, and the edges, which are like the links between the processors, and the edges just like are links that tell you which processors can communicate with each other in one hop. And we measure, communication through those hops. So we want to say like if an algorithm was described for topology A, which is really graph A for some communication network, how well is it going to run on graph B, which is another communication network? Yeah, so that's embeddings. Okay, so we're going to use hypercubic permutations a lot. And for this class, the goal is that we're going to, given a source topology, we're going to try to map it into a hypercube because we have a lot of algorithms that run well in the hypercube, like using that kind of communication pattern. So again, a hypercubic permutation is one where the processors that communicate differ in only one bit in their rank. So, like for example, if you have one bit, it's just 0 and 1. If you have 2 bits, 2 to the 2 is 4, and 0, 1 connected to 0, 0, and 1, 1, which differ in the first bit and the second bit, starting from the right. And then again, like here, this differs in 1 bit from 1, 1 and 0, 0. And a 3 cube is a full cube like this, where you have 3 bits, so you have 8, 2 to the 3, which is 8 processors, and they are connected like in a cube fashion. And then it goes up to higher dimensions, but those are hard to draw. And specifically, we're going to focus on relaxed hypercubes. So relaxed hypercubes are hypercubic permutations are when you do the communication, the bits. So you have to flip bits. Like in one round, you can only communicate with the thing next to you, and that has to change by 1 bit. But the different processors in relaxed hypercube, they don't have to communicate with the same bit flipped. So for example, let's say that 0, 0 and 1, 1, we're trying to send something. So in a relaxed hypercubic permutation, 1, 1 could send to 0, 1, which is flipping the top bit, but then 0, 0, I guess in this example is, yeah, so then 0, 0 would also send to 0, 1, which is flipping the bottom bit. In this exact example, it's serialized because like if you send 2 things to one processor, it has to serialize the receive, but it's just an example like that. You can, in the relaxed hypercube, send it like this, but that's like in the algorithm. Like in the actual connection network, they're still connected to things that differ by 1 bit. It's just like you can set your communication to things that differ by 1 bit, but it doesn't have to be the same bit for every processor. Does that make sense? Yes. Oh, I see. Yes, thank you. So there's a difference between like a hypercubic network and a hypercubic communication pattern. The hypercubic network supports hypercubic permutation patterns, but like there are many hypercubic permutation patterns depending on the algorithm, like the permutation pattern is just saying like who is sending to who at every step of your algorithm. And this relaxed hypercube is about the communication pattern, not about the underlying network. The underlying network is always fixed, like in this. The underlying network is just this connection of like nodes and edges. Yes. Yeah, exactly. Thank you. So yeah, so the underlying network, it only is every node is connected to things that are only one bit different from its own rank, and in the it can support relaxed hypercubic permutations, which is that every processor still you can only send to the thing with only one difference in bit from you, but it does not have to be the same thing for every source processor.
What we used before, was it less hypercubic implementation?
It depends on the algorithm. So, like,
We were using like for the NPF primitives, like communications, like we were sending to the neighbors. What were those?
um, those are I guess most of those are strict hypercubes because so in those usually you fix the distance. Like in each round, you either send like distance one or distance two or distance three or so on, or sorry, distance one, distance two, distance four, and the distance is determined by the bit that is set. And so if the distance is fixed within the round, then the same bit is flipped for everyone. So in those, that's like strict hypercube where the same bit is flipped for everyone. But it's like a more general class of permutation patterns. Does that make sense? Right. So people are good with this? Okay. So in this class, we're going to try to map some types of graphs into this type of graph using like a function. Right. So like I said, embeddings, you have a source topology A, which is really a graph. You have a target topology B, which is really another graph. And you want to define some function f such that you map like the nodes of A, which are ranks, into the nodes of B, which are also given ranks. Yeah. And so like I said, suppose that you read a paper and the paper gives you an algorithm that assumes some source topology A, but you have target topology B, and if you had a mapping, you could run the algorithm, the same algorithm that was given on this source topology A, and then use the mapping to actually run it on the target by just like using some function on the ranks. So you're not actually like from the point of view of the algorithm, you're still running it as it was described. You're just like applying some function onto the rank number, and then that is mapping it onto a different node. Yeah. So yeah, the source and the target are graphs, and we are interested for the entire class. The target is going to be able to support relaxed hypercubic permutation. So there are several performance metrics for embeddings. So we have a source graph VE, G equals VE, V is the vertices, E is the edges, and we want to embed it into a target graph, G prime, E prime, E prime. And so there are different metrics. Some have to do with the vertices and some have to do with the edges. So these have to do with the edges, congestion and dilation. And congestion is the maximum number of edges that are mapped, the maximum number of edges from E that are mapped onto a single edge in E prime. And that means like if you have two distinct edges in the original source and they get mapped onto one edge in the destination, then like when you run the source algorithm, then those would get mapped to the same edge in the destination. So you may get two processors trying to send along the same wire. So that's why it's called congestion, because you get some delay potentially if you have two processors trying to send along what they thought were different wires in the source. But now so this example, let's say these are two wires like blue and red, and then they get mapped to like this thing. The dots represent blue, these are blue, and these are red. And now it's getting mapped, both blue and red are getting mapped to this edge. So that is congestion. And then for dilation, that is the maximum number of edges in E prime that any edge in E is mapped to. And so here dilation would be 2 because originally blue was 1, but now it becomes 2 of these edges. So yeah, it's important to note that one edge does not have to map to one edge in the target. And the communication would slow down in the target by a factor of congestion times the dilation. Yes.
Basically, what would that mean? Like whatever node that existed, or whatever node that existed after that first edge, like an intermediate node that we introduced, because that wouldn't exist in the original.
that may exist in the original graph. So like, for example, let's say this was like U and V, like this. And then now like it maps to like U prime and V prime. And there may be some W prime in here that is like some other node in here. Yeah, so it doesn't necessarily have to be not in here. It just has to be, it was just like W prime was not between U and V, or W, W which maps to W prime was not in between U and V in the original source. Good question. Yeah, so it's a bit complex because uh, like I said, an edge does not necessarily map to another edge. It may map to a path in G prime. And if you have a path, well, no matter if you have a path or not, an edge in E prime may have multiple paths going through it. And that's just congestion. And then the second set of metrics has to do with vertices. So the first one is due to edges. We have the load, which is the maximum number of nodes in V that map to a single node in V prime. And then expansion is the ratio of the number of nodes in V prime mapping to those in V. So the computation would slow down by a factor of load. So like here, for example, you can map two edges U and V to a single node U prime. And then U prime would just run all the things that U and V were responsible for. But however, like if U and V are trying to do things in the same round, then it would be serialized in U prime. So then the performance would go down. So that's why, like, so for example, here the load would be 2, because U and V, two nodes are mapping to one node. And here computation was slowed down by a factor of load, because now U prime has to do everything that U and V were doing. Yeah. And if you have expansion greater than 1, which is you have more nodes in V prime than you did in V, then it's a waste of resources, because it's a bit hard to think about, like, it's hard to imagine why you would really need to map more, like fewer nodes into more nodes, because yeah. Questions? Make sense? Okay. So a mapping is just a specific case of an embedding where the load and the congestion and the dilation are 1. So there's like a one-to-one mapping between the vertices and the edges. And yeah, like I said, we're trying to map into the relaxed hypercube. So we ideally would like to make mappings rather than general embeddings because they have these nice properties about the performance of the embedding. Yeah. Some nice things about mappings also, you only need to, if you have a mapping, you only need to specify the node mapping because the edge mapping comes along with it. Because like if you have node U mapped to U prime and V mapped to V prime, then the edge between U and V directly maps into something in U prime and V prime. And another really nice thing is that the parallel runtime on the target is the same as that on the source. And the efficiency is preserved when the execution of the algorithm goes from the source to the target because you have this property about the dilation and the load being 1. So, sorry, the dilation, congestion, and the load being 1. So again, remember that communication was congestion times dilation. So 1 times 1 is 1, and the efficiency is the same. And that is not to say that the algorithm is efficient. Like if an algorithm was inefficient in the source, it's going to be inefficient in the topology. It's just to say that it will preserve the same efficiency. However, it's possible that there could be a target. We'll see some examples, but if you designed an algorithm specifically on a target topology, there could be better efficiency on the target topology. And we'll see some examples of that later. So like the efficiency is the same in the source and the dest, but if you design specifically for the destination, you may be able to come up with a better algorithm. And yeah, and if it's designed for the source, if it's optimally efficient, then it would be efficient on the destination. Okay. Any questions so far? So yeah. So first, we're going to talk about the most the simplest kind of topology, which is an array. So on the left side is a linear array, which is just your ranks are like left to right, and they're connected by links left to right. only like the neighbors are connected, kind of like a linked list in some ways. And then B is, it's like a ring, which is just the same as an array, but the ends are connected around. Like the easiest kind of topology. Okay, and this is how we would embed it into Hypercube. So suppose that we had the ranks in the ring, like 0, 1, 2, 3, 4, 5, 7, like that. And we are going to map it into not exactly the same. So like the easiest, most obvious thing that you might do is like you map it directly into its own rank. Like 0 becomes 0, 1 becomes 1, 2 becomes 2, and so on like that. However, the problem is that that doesn't respect the hypercube because the things next to each other may not be only 1 bit away from each other. So like, for example, I don't know, any of these examples, like 3 and 4 are not 1 bit away from each other in the representation. Like, oh wait, no. Yeah, 3 would be like 0, 1, 1, and then 4 is like 1, 1, 0, 0. So that's like 3 bits different. Yeah. So instead, we're going to map this in this example like this. 0 becomes still 0. 0 and 1 are still 0 and 1. But however, 2 becomes 3 rather than 2. 3 becomes 2. 4 becomes 6. 5 becomes 7. 6 becomes 5, and 7 becomes 4. And the nice property of this is that everybody differs by 1 bit from their neighbors. So 1, 1, 1, 1, it differs in the second bit from 1, 0, 1, and it differs in the last bit from 1, 1, 0. Yeah, and I guess I answered this question already. Why can't you just directly map the source into the target? Like, just make everything itself in the target is because they're not connected in the target topology necessarily. You do it like that. Yeah, so where did we come up with this? Well, if you know about grade codes, do people around here know about grade codes? Okay, well, this is exciting because grade codes are kind of cute. Okay, so grade codes are a binary ordering of numbers such that any two successive values differ in only 1 bit. And there are many kinds of grade codes, and they're usually used, they appear in all sorts of random places, sometimes in like error correction or something like that usually, but here we're going to use it for embeddings. So these are the binary codes, 0, 0, 0, 1, 0, 1, 0, all the way down. And these are the grade codes that we assigned them in the previous slide. And you can see that these are all flipping only 1 bit to get to the next one. 0, 0, 0 becomes 0, 0, 1, 0, 0, 0, 0, 1. You flip the second one, you get 0, 1, 1. Then you flip the last one again, you get 0, 1, 0. You flip the first one, you get 1, 1, 0. The last one, 1, 1, 1. Flip the second one, flip the last one. Yeah. And so how do you make those? Recursively. So the base case is you have 1 bit and you have 2 processors. And like I said, like if you remember, even in our bigger example, 0 and 1 had been assigned 0 and 1. And then how are we going to make these? So how do you make these 2 bits? Well, the higher bit needs to be set. But we can't just directly copy it across this line. Like it can't just become 0, 1 again, because then it would be like 1, 0 right after. It would be like 0, 0, 0, 1, and then 1, 0, which is wrong because 1, 0 differs in 2 bits from 0, 1. So these are called binary reflected gray codes. And so like reflection means that you would just flip it across this line. So you'd have like in the lower bit, you'd have 0, 1, 1, 0, and then you would put 0, 0, 1, 1 across the reflection. Yeah. So yeah, like I said, you reflect it, like you kind of think of it as there's this line after the space case, and then you flip it across this line like that. So the lower bits are 0, 1, 1, 0, and then the first half you unset the highest bit, and the second half you set the highest bit. And so the lower bits here, like all of them will be repeated again, just in reverse order in the bottom half. And then the bottom half has the highest bit set, and the lower half has the lowest bit set, so those are all different numbers. Yeah. then if you have a gray code for B bits, how would you preserve that? How does this preserve the property that it differs by 1 for B plus 1 bits? Well, it's clear that it differs in the lower bits, because you just, if it's true for the upper half, then you just reflect it across, and then the lower bits also hold the property in the lower half, because it's just the same. Yes. Yeah, so, okay, so in p equals 2, we just had 0 and 1. And then in p equals 4, just ignore the top bit for a second. What are the lower bits here? It's like 0, 1, 1, 0. So we flipped, this is 0, 1, and then we flip this, so it becomes 1, 0. And then in the top half, but now you need 2 bits, because you have p equals 4. So you set the top bit as 0 in the first half, and then you set the bottom bit as 1 in the second half.
So there's no, for the most significant, there's no reflection in the right?
Yeah.
Like the order is 0, 0, 1.
Yeah, because we're trying to go from B to B plus 1 bits. So when you have B, there's the most significant, there is no like most significant bit for B plus 1, like you're adding a most significant bit. So for the least significant bits, is it clear that, like, ignoring the top bit for a second, is it clear that if you reflected it, the top half would be all different, like all differing by 1, and the bottom half is all differing by 1 as well? And so, but that doesn't cover the entire space, because then you have repeats. So you put 0 in the first half, which is, it would be like if you put 0, 0, 0, 1, that would be the same as this. So this is, the top half is just the same as what we had here. But now the bottom half needs to change, because you cannot just repeat the first half again. So we put 1 in the top bit, because that would give a covering of the entire 2 to the b plus 1. Yep. All good? Yeah. So that is how you make a gray code for b plus 1 bits from b bits. You just define it recursively. We start with 0, 1, and then you just, I guess here we're going from like in the forward direction, but you could also think of it in the backwards direction. Yeah. And then going back to the full example that we had, p equals 8. So now we take this 4 here, 0, 0, 0, 1, 1, 1, 1, 0, ignoring the top bit for 1 second, 0, 0, 0, 1, 1, 1, 1, 0, which is exactly this. You flip it here. So now 1, 0 becomes 1, 0 here again. 1, 1 is 1, 1. 0, 1 is 0, 1. 0, 0 is 0, 0. And like I said, the top half, the upper bit, most significant bit is 0. The bottom half, the most significant bit is 1. And that is all 8 numbers. Yeah. And then if you wanted p equals 16, you would just do the same. You flip it again. That make sense? Okay. So yeah, so we're going to use that function. We're going to use gray codes as a function to map arbitrary linear arrays into the hypercube. So if you have a ring, well, let's just say we have a ring, because a ring is stronger than an array, and you can always map something stronger into something weaker. So you have a ring or an array, and you have 2 to the d nodes, 0 up to 2 to the d minus 1. You use gray codes GID, where d is the number of bits into the hypercube. So, and this function is like this. So the base case again, 0 and 1 is 0 and 1 here. And this is the recursive definition. So if you have I is the rank, x plus 1 is the number of bits, and g of xi plus 1, recursively defined, is gi of x when you're in the first half, so I is less than 2 to the x. So you have x plus 1 bits, so you can say it as like 2 to the x and 2 to the, sorry, you have 2 to the x plus 1 numbers if you have x plus 1 bits. And so x plus 1 number, 2 to the x plus 1 numbers is like 2 to the x plus 2 to the x. So the top half is 2 to the x, which is this. So the top half is just given by the gray code for ix, and the bottom half is given by the gray code 2 to the x plus is just flipping the top, just setting the top bit, and then this is the reflection. to the x plus 1 minus 1 minus I. So like as I is going up, this thing is going backwards. And then the last bit is x, because we defined it on the gray code for x bits when you have x plus 1 bits. Yes? Oh, ring is just, it has like the thing connecting the beginning and the end. Yeah, that's the only difference. Yes? Yes, exactly. Like it can do everything that an array can, except if you like an array, if you wanted to send from the end to the beginning, you have to go all the way through. But in a ring, you can just go around. Yes. Yes, it is not. This is not supporting a ring. This is supporting a hypercube. It is how you map a ring into a hypercube. So like in a hypercube, all the neighbors that are connected are differing by 1 bit. So here, the neighbors that are connected differ by 1 bit. Uh-huh. Sorry. So here, you're saying like in the hypercube, 0 to 7 here, originally you needed 3. Or sorry, in the hypercube you need 3 because you like 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1. But here you need more than 3. Um, yes. So it may not be optimally efficient, I guess. Like this is saying, so embeddings, like as you can see in this example, like sometimes they preserve the property like it's exactly like in the hypercube. So a ring is less strong than a hypercube. So like here, 0, 0, 1, like in the hypercube, 0, 0, 0, 0, 0 would be connected to this one, and that one. But however, as you can see in the ring, like they're obviously not all connected. So um, this is just like if you had to map this ring into a hypercube, then you would simulate the communication through those links. But it may not be like exactly 1-to-1. You see that with more connections. Yeah, good point. Yeah, this is just it's a way to simulate, like it doesn't go backwards necessarily. Well, I guess you could invert the gray code and then you could go backwards, but like this exact function is not going to go backwards directly. Yes. Okay. So assume that you have these entries, GID and GI plus 1D, those are gray codes, and they differ from each other by only 1 bit position. Corresponding processors get mapped into neighbors into the hypercube. And then what is this? Well, the load is clearly 1 because every processor gets mapped to one other thing. And then the expansion is also clearly 1 because the ratio of processors in the source to the ratio of processors in the disk is also 1. Congestion? Well, so we're not mapping. So like the congestion would be greater than 1 if you were mapping a hypercube into the ring, but you're mapping a ring into the hypercube. So the properties are protected with this reassigned mapping from the ring into the hypercube, but not from the hypercube into the ring. Because like what you were saying, in the hypercube, as you said, like the things that were distance 1 are no longer distance 1 in the ring, but we are going in the opposite direction. So for the forward direction, all are 1 because the things in the ring are neighbors of the thing in the like the things that were neighbors in the ring with this gray code assignment are neighbors in the hypercube. But it's not necessarily true in the reverse. That if you had a full hypercube, the things that were neighbors in the hypercube are not necessarily neighbors in the ring because the ring is weaker. Does that answer your question?
The neighbors in the ring are not have one case that you don't have. They're not really neighbors.
0, 0, 0, 1, 1, 0.
Okay.
Yeah. So all the yeah. So yeah, this is a really important point. But yes, so thank you. With this assignment, everything that is neighbors with this gray code assignment are neighbors in the hypercube if they differ by 1 bit. But it does not work in the reverse direction, which is if you had a full hypercube, everything that is a neighbor in the hypercube is not necessarily a neighbor in this ring because here the ring only has 2 neighbors each, and we have 3 bits. So in the hypercube, everything would have 3 neighbors each. So clearly it doesn't line up, but we are only going in the forward direction. Like we map only in one direction at a time, and from the ring to hypercube direction, everything, all the properties were 1 because all the neighbors are still preserved, and the edges are still mapped 1 to 1, and the nodes are still mapped 1 to 1. Yes.
Why is there no dilation?
So this is not so like this ring is not supporting a full hypercube because this is okay. So yeah, sorry. So if you have a source, which is the ring, we have it. So you have an algorithm designed for a ring, but we ourselves we have a machine that is a hypercube, and we with our hypercube want to run the ring algorithm. We don't have to use all the edges, and this is not going to use all the edges in the hypercube because clearly a hypercube with 3 bits would have 3 edges per node, and this only has 2 edges per node. So we're going to use a subset of the edges. But we're just going to say we can run the ring algorithm efficiently when we have our own hypercube. Yes. Here the mapping, here this is a mapping, which is like a 1-to-1 function. So all the properties, congestion, dilation, load, they're all 1. Yeah, so this part is a bit confusing, which is this is not going to support the full hypercube, but it is just that we have a hypercube and we don't want to completely redesign the ring algorithm for our hypercube. So we're going to pretend we may not use all the links. And as you can see, this is not all the links in the hypercube, but we're going to run the algorithm on some of them. We're going to pretend that some nodes in the hypercube map to some nodes in this ring. Okay.
Is there a metric that pertains to link utilization? Right?
Yes, there is not in this none of these. Those are all they're kind of like link utilization from the source in some sense, but not really. Everything in the every edge in the source has to be mapped into every edge of the desk, but all the edges in the desk are not necessarily used. Yeah, good question. Not that I know of, but maybe there should be. I guess if this is you have something weaker, so you can only make it. You can always make it run on something stronger, and we just don't use everything in the stronger topology. Cool. Okay. Yeah, and this is just the example that we had. So you have 1 bit, 0, 1. You have 2 bits, 0, 1. Flip them, it becomes 1, 0. And then the upper bits are 0, and the lower bits are 1. Or sorry, the highest bit in the first half is 0. The highest bit in the second half is 1. And then you extend that to 8 bits. So you flip it again over the axis. You set the first bit in the top half to 0. You set the first bit in the bottom half to 1. And then those are all 8 numbers, just not in exactly the initial order 0, 1, 2. They're now in this gray code ordering. And they all differ by 1 bit. And yeah, these arrows are showing the connections that are used by this ring. But you can see not all the edges have an arrow next to them. Yeah. So this is what we have, and this is how we're going to simulate the ring. Yeah. And then so you formally when you actually run the algorithm, you have this function which is G to B, which is gray code to binary. And then this is how you get the left neighbor and the right neighbors. So you just do this bit manipulation. Yeah, so you have an algorithm that is described for the ring in terms of ranks. And so to run the algorithm, you need to run whatever rank R was doing in the initial algorithm, the gray code ordering of R needs to do it in the target. And then it needs to go back. So yeah, so if you had, for example, rank 3, the rank 3 in your target, the ring rank that corresponds to that, the binary thing corresponding to number 3 is 2. Like, the hypercube has 3, and then the ring was 2. So the ring rank corresponding to the third rank in the hypercube is 2. The left neighbor in that is 1. And then the right neighbor is 2 in the hypercube. Yeah, so 3 was this, and then left neighbor is 1 pointing into here, and then right neighbor is 2 pointing that way. Questions? Okay, so ring array is, or like ring topology is not really that realistic because it's not very strong. So in reality, actually, sometimes you may be interested in mesh topologies. Excuse me. Because like if you, for example, if you have matrix algorithms, often it is useful to think about your topology like a mesh because you cut up your matrix into blocks. Like you have a 2D matrix and you cut it up into 2D blocks and you put one block on every processor. And we will do matrix algorithms in a little bit, but it is sometimes nice to think about mesh topologies like this, which are just like 2D or 3D extensions of ring or array. So like this one is a 2D extension of ring because you just kind of like you have is a 2D extension of array. Like you have one array and you just copy it. And then you also like every row is an array and every column is an array. And then same for this one, but it's just for ring. Like every row is a ring and every column is a ring. Yes.
We'd immediately know that there is like is like the degree of like there's like even with just 2 rows, then we could and the hypercube only supports.
Oh, no, good point. So now we have 16 nodes rather than previously we had 8 nodes. So that's why the degree was 3.
Oh no, so I was saying like if we just if our network was just like the first 2 rows of the top, like for 8, we had 8 processors.
Yeah. But if you had 8 processors, the degree would be like 2. Or I guess 3 in the middle parts.
Oh, okay.
Oh yeah. So like I guess like if you just have the first half, ignore these links here because those don't exist anymore. So like this one would be connected to this one, and that one. Yeah. So yeah, the reason that this still will work in the hypercube is because the more nodes you get, the higher, like the more degree you get also. And the degree, I guess no matter how many nodes you have in here, like it could be like 8 by 8 or something, but the degree is not going to change when you get more nodes in the mesh. So this is 2D, which is just you copy the ring, and every row is a ring, and every column is a ring, and then it can also go to 3D. So like every X, Y, Z is an array. Yeah, and dimensions need to be a power of 2 because gray codes, like the way that we're doing the gray codes, it's like a power of 2. Okay, so how are we going to extend what we had for 1D into multiple dimensions? Well, we have an algorithm to do it in 1D, and every row is 1D and every column is 1D. So we can think of the rank indices in 2D as like a pair. It's like x and y coordinate. And basically the way it's going to work is that we're just going to concatenate the x and y coordinate into one single binary string. And yeah, so for example, like 0, 0 is here, 0, 1, 0, 2, 0, 3. And the binary code for 0, or sorry, the gray code for 0, 0 is 0, 0, 0, 0. The gray code for 0, 1, 0, 0, 0, 1. The gray code for 0, 2, this thing is not 2, this thing is 3. Because the gray code for 2 was 3. So that's why this is 3 here. And then here, like the gray code for 3 is 2, because we reflected it. So just look at the first row. We got this 4-bit binary string by taking the gray code for the top, for the x coordinate, taking the gray code for the y coordinate, and putting them together. And that's how you get like, if you have d bits in one dimension, you're going to get a 2D bit string for the entire 2D mesh, because you have x and y. And this is just more general, like 2 to the r to the s. It doesn't have to be a square necessarily. Yeah, this is just bit concatenation. Does that make sense? Okay. Oh yeah, how does this preserve the gray code property? You still want every neighbor to differ by 1 bit. So if we use the scheme, how would you show that you still preserve the property that you differ by only 1 bit? Yes.
Only either move the x to y axis.
Mm-hmm. Mm-hmm. Good. Exactly. Yes. So either when you move to the neighbor, either the row or the column is fixed. So you're only going to change in one of either the upper D or the lower D in this example. Or I guess in general, the upper R and the lower S. Yeah, this is just how you do the bit manipulation. The first, if you have R bits for the row and S bits for the column, X is the first R bits, Y is the lower S bits, and now you have some things. Before we only had left and right neighbor. Now we need to do left, right, up, down neighbor. And if you move right or left, Y is not changing. Like you said, you only move in either the row or the column. So this thing is in the row, the first one. And this is just exactly what we had for the left and the right neighbor, except now we have mod. And north and south, it's the same thing as we had for the left and the right neighbor for the ring, except now it's on the y part rather than the x part. So this is an example. Suppose that we had this 5-dimensional 1, 2, 3, 4, 5 thing, 5-dimensional mesh topology, and you can see that every one of these is a power of 2. So that is 2 to the 13. You just multiply them all together, and we have 5 to the 5. Oh yeah. Suppose that we wanted to map this rank. So 5, 2, 3, 1, 7. This is just the rank in each of the dimensions. And then you would do that, you concatenate the bits. So this is 8 dimension, or sorry, this is length 8, so it would have 3 bits. This is length 4, so it would have 2 bits. Length 16 has 4 bits. Length 2 has 1 bit, and then length 8 again has 3 bits. And how do we get these bits? Well, we map the initial rank in the dimension into the gray code. So like 5, the gray code for 5 is 8, 7, sorry. This is 5, this is 7, so you would put 7 here. And so on for the rest of them. And we don't have, this table only goes up to 8, but the thing in the 16, this thing in the long dimension happens to be in the first half. So this table is the first half of the 16 table. So 3 goes to 2. So that's why it's 2 here. Mm-hmm. This is 5 dimensions, but yeah, this is 5 dimensions, and each of these is the length in that So like 8 is the first dimension length, 4 is the second dimension length, and so on. But the scheme generalizes to arbitrary dimensions. You just keep concatenating the bits. So like the first dimension was 8, and suppose that, so the for arbitrary dimensions, like for d dimensions, you can describe the rank with a d bit with a d length tuple, where the entry in every tuple is just like the rank that you're considering in that dimension. And the way you do that is you do the gray code for whatever is in that dimension, and then you just concatenate them all. So 5, the gray code here was 7, so that's why we put 7 there. 2, the gray code is this one, so you have this one, and then so on like that. Yep. Yeah, so the congestion, dilation, expansion, and load are the same as they were in the ring because it's mapping. Like the same property, it's like the same property. The degree again is fixed. Yeah. And like I said earlier, if you could define an operation directly in the target topology, you may be able to define it more efficiently than if you simulated it in the source topology on the target topology. So for example, consider a broadcast. Let's say we had a 2D mesh, like just n by n. How long would it take us to do the broadcast in the square mesh? Or sorry, square root n by square root n, I guess. So we have n total processors, and let's say it's a square, so there are square root n rows and square root n columns. So let's just take one row, like, and assume that you can just hop one link per round. So it's gonna, how many rounds is it gonna take us to broadcast in an entire row? Yeah, I guess square root n, because like the row is square root, but yes, yeah. So it's lower bounded by square root n, assuming that the side length is square root. But however, like if you had an n, like you have an n processor hypercube, we know that we can do it in less than square root n, like log or something. Yeah. So if, yeah, so it would take at least square root, I guess p, where p is the number of processors in the entire thing, and square root p is the number of processors in the row. That's going to take root p in the mesh, but it's going to take log p in the hypercube. So we could, like, we have an algorithm for broadcast in the mesh, and we could run that algorithm in the hypercube, and then we would have also run broadcast. But if you directly had a hypercube, we know that we can do broadcast more efficiently by making use of more links, basically. Like we saw in the example, the mapping is not using all the links in the hypercube, and if we could use all the links, then we could do better. Yes. What would the broadcast be for cube mesh? If you have p, then it would be like 3, like cube root p. Yeah. That makes sense? So yeah. So like I was saying in the beginning, if you had an efficient algorithm, like your algorithm in the source is going to run in the same time as the algorithm on the target if you have a mapping, but it is not necessarily the fastest algorithm that could be on the target. Questions so far? Yes.
Let's say the data is 0, 0 in the beginning. So if the root p means here there are 8 processors. So if the root of like if you take this here like 3, right?
Sorry?
You said like the broadcast can be done in root p operations. So if you do root of 8, and even if you take the seal of it, it will be 3 or something. And here, but how can the broadcast be completed in motion? Because you can see 0 can then to 0, 1, and 1, 0. Again, from 1, 0 to go all the way to 1, 2, 3.
Yeah, so like if you started here, it has to do at least 1, 2, 3 hops because you have to go from here to here. And then, so like in the first round, you would send here and here, or here and here. Sorry, I guess here to here. And then after that, everybody could do like this way. Like, kind of like in the hypercube, like once you send the information to another processor, like the other processor can help out in the broadcast. So the same idea can happen here. Yes.
Doesn't that mean that because we can turn a mesh or we can map a mesh onto a hypercube, then a mesh right? They give that back.
I think it's backwards because like if you remember when we did the array, for example, like the array could be mapped into the hypercube, but it wasn't using all the links in the hypercube. So, but however, like if you had an algorithm directly designed for the hypercube, you could use all the links. Like the array and also the mesh are using like a subset of the links in the hypercube. So it makes sense that you could not do it faster than you could in the hypercube. It's like you're not getting more links. Sorry, the source does not have more links than the destination has. It only has fewer. And so you could maybe, it doesn't necessarily mean that it's slower, but it means that it couldn't really be faster, probably. And so, yeah, so like this is root P because if you had a square, like you have to at least go all the way down the row, and the row is going to be root P. However, here, this is log because we know that we can do log broadcast in a hypercube. Like you kind of do like, you have a root, and then root sends it to someone, and then those two, like the number of processors participating in the broadcast doubles every round in the hypercube. But it's not happening here in the mesh because the links aren't set up that way. Yeah. Yes, exactly. Yeah. So that, yeah, it's confusing, but you gotta keep the direction straight, which is you have a source and you map it into the target, and you run the algorithm designed for the source, simulated on the target using like the bit manipulations.
So even though there's like, for example, the node in the first column, the last column, you wouldn't be able to use that. Like the algorithm that we're using know that like edge exists, like between 0.
Like this one and this one.
Yeah.
Yeah.
That one.
Yeah. Yeah. So you wouldn't know. Yeah. So because this is a mesh, so this wouldn't exist in the mesh, even though it does exist in the hypercube. Yeah. Good question. Yeah, it is confusing. So you just got to keep the order straight. Yeah. So the last thing that we're going to do is mapping binary trees into hypercubes. And the reason that we are interested in doing that is that some algorithms are well suited to binary tree topologies. Like, for example, it's easy to see the broadcast algorithm in a tree. Or for example, like sometimes in image processing, you have like an image and you cut it up into quadrants recursively. So every level of the tree is like cutting up the quadrants, and then at the bottom you have like the pixels. Okay, so we want to try to embed this binary tree into hypercube. So suppose that you have p leaves in your tree. So you have overall 2p minus 1 nodes in the entire binary tree, and you're trying to map it into a 2p node hypercube. And we're going to make an initial argument that, so an initial way that you could do this is like you assign the root to someone, and then you assign the two neighbors to like two things that differ in 1 bit in the hypercube. Sorry. So, for example, like you assume that the root is mapped to someone with an even number of zeros. For example, 0, 0, 0. And then the next level has to be mapped to something with an odd number of ones, or an odd number of zeros, I guess. Because like, for example, you have like 0, 0, 0, and that would be like 0, 0, 1 and 0, 1, 0. Something. Like you could, a natural way to map this into the hypercube is that you just keep flipping one bit at each level. So then the parity would be like even, odd, in terms of number of zeros. And then every alternate level starting from the root would be mapped to processors with an even number of zeros. So like even number of zeros, odd number of zeros, even number of zeros, odd number of zeros, so on like that. And then the entire leaf level would be mapped to target processors with some parity, either even or odd number of zeros. Doesn't really matter. The number of processors of that same parity required is P, which is the root, or P, which is the leaves, P over 4, which is one level up, so on like that, which is greater than P. And we know that we already have only P nodes with the same parity. So this initial assignment is not going to work. Does that make sense? But there was an assumption in here, which is that we had to map every level to the same parity. We don't necessarily have to, so maybe we can relax the assumption and then do some kind of mapping to like some even processors and some odd processors can be at every level. Yes.
Why did like the previous way we did broadcast, like why wouldn't that work as a binary? Isn't that a binary tree as well? What do we need to do?
Why do we need to?
So like in the previous we had like we just mapped it to our neighbor at that certain level. Like that's a binary tree as well, right?
Yes.
So like what's the difference between compared to that? Like is this more efficient or
previously in the binary tree, you map to your neighbor, but the neighbor has opposite parity from you. Oh, you're saying like you map to your neighbor and then the next one you also continue. Yeah, we're gonna do that and then yeah. But it doesn't necessarily work for general algorithms because it assumes that your algorithm runs in that specific type of phases. Like for arbitrary tree algorithms, that wouldn't work. Like if you had, like broadcast is nice because it can happen in those layers, but arbitrary tree algorithms may not necessarily happen in those layers.
Oh, okay. Yeah. So like that would only work for something with like breakfast search versus.
Yeah, exactly. Like that kind of similar communication pattern. But as we saw, like many of like all those primitives that we saw kind of follow similar, not exactly the same pattern, but like similar phase pattern. So yeah, we're gonna do that. We're gonna get there in like a couple of minutes. But yes, thank you. Yeah. So we assumed that every processor in the same level had the same parity, which does not necessarily need to happen. Like for example, in when we do broadcast, like we start with 0, 0, 0, and then in the next round we have 0, 0, 0 and 0, 0, 1, and then both of those participate in the next level and so on like that. So we're just going to try to apply the same idea. Yeah. So how we're going to fix it? We can split. Yeah. So one intermediate idea is that we can split the even and the odd in the children. Like they don't all have to be the same parity. However, the problem is that the dilation may be 2 because you have to go through 2 links rather than 1. Because if you are even, like 0, 0, 0, and you're mapping to another even thing, like so 0, 0, 0, 0, and you want to map to the same parity of zeros, which becomes 0, 1, 1, for example, that would be 2 links. So this is 3 zeros, this is 1 0, so both have odd number of zeros. Yeah, so then the dilation may become 2. Actually, practically, it may be fine to have dilation 2 because like you don't actually, like when you think about the communication, the way that we talk about communication, like in terms of mu and tau, like the dilation doesn't really show up there. Like if we're not doing round, if you don't have to do another round of communication, like you're not sending more bits, which is going to affect mu, and you're not adding more tau. But as we were just saying earlier, like it doesn't have to be this complicated. If you know that your algorithm has some property, we could just do like the broadcast type topology. Yeah. So most tree algorithms are level by level, which is that like broadcast, like all the levels are serialized. Like every level has to happen one after the other, but everything within the level can happen in parallel. And so like just doing the same with broadcasting, we just reuse the processor across the levels, like we did in broadcast, but this only works if your algorithm is of this form. where it happens level by level. And then you can sequentialize and reuse that processor. Yeah, does that make sense? Okay. So formally, how are we going to do it? Well, you have P processor. Let's say we have P processors in our tree, and P has a power of 2. And we're going to do computation is across every level in parallel, and the communication happens between the levels. And the tree has log p plus 1 levels, and the root is at 0. Level I has 2 to the I nodes, and then they're just numbered left to right like that. And here, like, this is the same broadcast tree. Like 0, 0, 0 is up here, and it's just being reused along this path. And then again, like 1, 1, 1 is here, or sorry, 1, 0, 0 is here, and then it's being reused here that way. And then that would happen for like this one would be reused over there. And so the rank is given by, if you have a tree node, ij, where I is the level and j is the rank within the level, then you can map it into some global rank by doing bit manipulation. So, and they're all going to be unique because like the upper bit is set by I, which is defined by the level, and the lower bits are just ordered left to right. So the rank overall would be j, which is your thing in the upper bits, and then zeros in the rest. Yeah, and then in the tree, you just get like this. The upper bits are the same, but you set 1 here in the lower bits, in the highest one in the lower bits. ij is connected to I plus 1, 2j, and I plus 1, 2j plus 1. So like they're kind of in like heap order, or yeah, they're in like heap order, or BFS order. And if you want to move around in this tree, the parent, you flip the bit to 0, because the way that we constructed this was that we set, so you can see we're reusing this part. This is the parent, and we're reusing the parent as the left child. And then on the right child is changing, but this is happening recursively. So like when this will also have 2 children like that, and then this one would be reused as the left child over there. And the way you get the parent is you change the relevant bit, like this one. You would set this bit to 0. You would just come back to here, and then left child is yourself, and right child is you flip this bit to 1. And that's how you would, this is just like the same bit manipulation that you do to get who's next in your broadcast. That's it. Questions? Okay, thank you.